Okay, so as a recap, to investigate what a sinusoidal function might look like or a periodic function might look like, we try to measure the distance that you would run around a track. Sorry, not the distance, your location on an Olympic track based off of, based off of the distance between the person who's running and a person that's timing you to the center of the track. Okay, so we graphed it and we realized it became this funky curvature, and that is what we call a periodic function because it repeats. I gave you some terminology last class, and now it's about time we learn what ways we model periodic functions. Specifically, I'm introducing to you to something called a sinusoidal function, and the name of it, as far as you might be concerned, it's pretty obvious of why we might name it this way. I need everyone to take out their calculators because we are going to be doing some punching in. So whether it's by your phone or if it's with a real calculator, I don't care, but you need to be able to do sine. With your sheet, step one, I would like you to measure out the labels based on this exercise, okay? For this particular exercise, I would like you to label each box in 30 degrees. Good morning. So let's pretend this is 30, 60, and then after 3 boxes, let's label it 90, 120, 150, and that is 180, 1, 2, and then 270, 1, 360. Okay. And of course, because this is a Cartesian coordinate, I'd like you to mark the other side as well. 1, 2, 3, and then negative 90. 1, 2, 3, negative 180. 1, 2, 3, negative 270, and 1, 2, 3, negative 360. So please notice, one thing that is different about this graph than any other graph is that I am marking degrees. But ultimately, as far as, let's say, as far as Desmos.com or as far as calculators care, it's still a number. Okay. Next, it says label the y-axis to increase by 0.25 units, in other words, a quarter. In short, count up 4 boxes and mark 1. Okay. 1, 2, that's 0.5. 3, 4, that's 1. 1, 2, that's negative 0.5. 3, 4, that's negative 1. And that's it. All that's left is to calculate. And do you have a calculator? Yeah? Please do the first 3. Hey, do you have a calculator? Please do the next 3. Zach, do you have a calculator? Please use the next 3. Nessica, do you have a calculator? Please do the next 4. And then we've got Kaylee, if you have a calculator, please do these 3. Plug in negative 360. Maria, if you have a calculator, please do these 3. Janae, you with me? Okay, if you have a calculator, would you please do these 3? And lastly, Brendan, if you have a calculator, would you please do these 3? Okay, very quickly, team effort. I want this filled in as fast as we can, and we will begin graphing. We will mark it all in red. Oh, sorry, maybe I didn't explain. Assuming that the function is sine x, what I like you to do is do sine 90 and tell me what it is, sine 120 and sine. We're essentially pretending that this was like, like a triangle, right? We're just plugging in what the number would be if we put in a variety of degrees. And remember, 0 to 360 is a full circle, right? I'd like you to keep that in mind. I'll say it one more time. 0 degrees to 360 degrees, you know that the degree 360 is equivalent to a full circle, right? Ready? What is your first number there? 0, okay, next. Sorry, let me do this so that it's easier to see. Okay, go for it. 0, 0.5, 0.9, 0.87. Next, Sage, you ready? Go for it. Right, so I'll round it because I don't have enough space. Interesting. Stop right there. Do you see something funny happening with the numbers? Maybe you don't. Let's keep going. Zach? 0. Negative 0.5. 866. So 87. Good. Nessica? Negative 1. Okay. Stop right there. Analyze your data. 0, it goes up by these two funky numbers and then a 1. And then it comes down with the same numbers and then 0. And then it goes even lower in the negatives, but it's still the same absolute value. And then a negative 1, and it comes back to a 0. Okay. Let's do the negatives now. Really?
0.
Okay.
0.5.
Oh. Is it 0.5 or is it? Oh, yes, you're right. My bad. My fault. Yep.
0.87.
Good. And then, where are we? Janae? I want to try again, but I'm gonna actually come back to it. I'm gonna leave it as blank. It's gonna be a great exercise. Oh, that's my bad. Who did this one? Maria, was that you? Oh, my bad. Go for it. Sorry, that's my bad.
0.87.
Oh, interesting. Do you see an interesting coincidence? Janae, go ahead. Oh. Yeah, you might want to check that. But okay, again, I'm gonna leave this blank, okay? And Janae, I want you to follow along after. I'm gonna leave that blank. It's gonna be a great exercise. I'm actually happy that this tripped up. Brendan, last 3.
I got -1. Negative 0.87.
Okay.
Negative 0.5.
Okay. And then it goes back to a 0 because you know -3, -30 degrees. The next degree is the next number that we're going to do is a 0. So take a look at the upper chart. Take a look at the next chart. What do you notice about all the numbers? Every single one. Please. Do you see it? Do you see it? You look at me like I'm crazy. Yep. It's periodic. It's repeating. Right? So even if you didn't get it, you know that after the 0.87 and it goes down to 0.5, it'll probably be a 0. It'll probably be negative 0.5. It'll probably be negative 0.87. Right? And it is. It's a continuous repeat of the same motion again and again. So we're going to graph it, and I'd like you to notice, and I'd like you to realize. Okay, let's start from the second chart. 0 degrees, 0. 30 degrees, 0.5. 60 degrees, 0.87. So it's going to be somewhere here. And then 90 degrees, and then back to 0.87, and then 0.5, and then 0 degrees. Looks a little bit like a parabola on this graph, but it's not. Let's keep going. After 180 comes 210, as that becomes negative 0.5, and then a negative 0.87, and then a negative 1, comes back. And I think you could imagine, if I continue this, it's going to repeat the same motion. Let's go to the left. Negative 30 degrees, I'm here, by the way, just in case you're confused. I'm starting here, and I'm going backwards, okay? Negative 30 degrees gave me a negative 0.5, that's down here. And then a negative 0.87. And then a negative 1, and then negative 0.87. And then a negative 5.5, and then a 0. And then 0.5, 0.87, 1, 0.87, 0.5, and 0. I know I'm moving fast, but once you start seeing a pattern, I think you'll move relatively quickly too. Using a highlighter. Different colors. Thank you. Yeah. Yes. And so this is what we call a sinusoidal. It is periodic. It's a periodic function, but we give this a very special name, sinusoidal, sine, because it is not, well, in the right now, all you might care about is essentially, we are using the sine ratio to calculate all of this. The curvature going up and the curvature going down, if I were to graph this correctly, would be a perfect half circle going up and a perfect half circle going down. And that sort of makes sense because I said earlier, 360 degrees is a full circle. So think about it like this. Another way you could think about sinusoidal functions is, imagine I'm going back and forth, back and forth, back and forth, back and forth, back and forth on a circle. But this rotation, instead of going up and down and up and down and up and down, if someone asked me, hey, go and graph that motion, well, isn't my height going up and down and up and down and up and down and up and down? Get what I'm saying? To go from here to the highest point, I go up, and then I go back to where I started, I go down, and then I have to go to the lowest point, which is going down, and then I go back to where I started, which is there. A sinusoidal function essentially models a circle, the motion of a circle, a perfect circle. That's it. That's literally it. Put a little star next to this, okay? Because this is going to be really helpful for part 1 of the assignment. I'm literally asking you to graph the most detailed sine curve possible as part of the assignment. Okay, and while it's perfect timing, while we wait for our guidance counselor visit, I want to mention a couple of things. There are some things that are, what is it? There are certain periodic functions that are sinusoidal, but periodic functions that are not sinusoidal. To just be able to distinguish between the two, take a look at two examples that are not sinusoidal, like this. Question, is this graph periodic? Yeah, it repeats right here. So this portion will repeat, yep, with this portion, and then it repeats again in this portion, so on and so forth. But it's not sinusoidal, because as I was saying, sinusoidal must demonstrate the curvature of essentially, what is it? What's the best way to describe this without confusing? Think about it, it has to be nicely curved and repetitive in that way. Okay, there's one curvature going upwards, hitting a maximum, and then it has to come downwards. Yes, it can go whoa, and then down, and then whoa, and then down, back up. However, it cannot sort of change directions in that way. It's just one big loop upwards and one big loop downwards is what we would consider sinusoidal. The technical way is a sinusoidal function can be expressed using the sine ratio. It has to have some form of sine x in there when we model it. Any questions? Okay, then I am actually going to pause this video while we wait for our guidance visit. I did assign people to try these questions, number 1 and 2. I will ask that you try 1, 2, 6 as well while we are waiting. And then once our guidance counselor visit is done, I am going to specify the chapter 6 assignment and what you could probably get started on. Okay? Actually, I don't need to record that part, so we'll stop the video.